here today to help you sort of sum up all of those main ideas that we've been learning so far in sections 4.1 and 4.2 about quadratic functions. There's been a lot of information, so I want to sort of help you just sum up the really big ideas because quadratics are awesome and they're really, really useful in everyday life. The text that we are using is, of course, Algebra with Models, A Guided Inquiry by Marian Anton and Karen Santora from CCSU. So let's get started talking about all these big ideas. What is a quadratic function? What are the important pieces of the graph of a quadratic function? Let's dive in and get started. So real quick review from section 4.1. Quadratic functions, what are they? We said that a quadratic function is defined by an equation of the form y or f of x equals ax squared plus bx plus c, where a cannot equal 0, right? And that's important because, look, if a equaled 0, then this entire piece would go away, right? It would be 0 times your input squared, which is just 0. 0 times anything is 0. And that would leave us with a line. So a quadratic function, the coefficient in front of your x squared term, it cannot be 0. All right? X is, of course, the independent variable or the input. Okay, that's where we're going to input some value. And y, or f of x, is, of course, the dependent variable, the output. So we input some x value, and we get an output, a y value for our function here. Then, of course, a, b, and c are constants. So these A, B, and C's, right? This a, b, and c right here, those are constants. We refer to them as coefficients, right? They're constant numbers, which just means that they don't change, okay? So this is what the general form of a quadratic function would look like. We also noted in our last lesson that ax squared plus bx plus c is called a second order polynomial. All that means is that the highest power on our variable is 2, right? So that is a second order polynomial. The highest power for that polynomial is 2, okay? And we discovered that when we looked at a table that we saw was a quadratic function table. So we said that quadratic function tables are tables of values characterized by constant second order differences of the output when the input increases by a constant. So we notice this second order keep popping up, right? Second order polynomial, the second order differences were really important, and we're going to talk about that more in a second. So let's take a look at what do I mean by those second order differences. Let's quickly review that concept. So again, let's quickly keep reviewing section 4.1. We discovered this idea of this second order. What did it mean, right? And what we were doing was we were looking at how the side length of a garden affected the area of a garden. And we discovered that when we had this table of values with those two variables, it was in fact a quadratic function. And how did we discover that? Well, we saw that our input was increasing by a constant. So if you look at the left side of my table, the side length s, every time we jumped from one to the next, right, we were jumping by 1 plus 1. To go from 1 to 2, you're adding 1. To go from 2 to 3, you're adding 1. To go from 3 to 4, you're adding 1, and so on, right? And then we looked at the output and we decided, okay, let's see if there's a pattern there. And when we checked, we found that it was neither linear nor exponential. We saw that the output was not changing by a constant or a constant multiplier. So when we did that, right, to go from 1 to 4, we added 3. To go from 4 to 9, we added 5. To go from 9 to 16, we added 7. And to go from 16 to 25, we added 9. And we called those the first order differences. When we made those first initial jumps, we said we gave them this name, the first order differences, and we did not see any sort of a constant pattern with those first order differences. But then we thought a little bit more and we said, but if I look at those first order differences, 3, 5, 7, and 9, right, I actually can see a pattern between those. In fact, to go from 3 to 5, I add 2. And to go from 5 to 7, I add 2. And to go from 7 to 9, I add 2. So, in fact, we can find a pattern now. And we call those the second order differences. So we may not have had a constant when we looked at our first order differences. But when we looked at our second order differences, we found this constant of 2. And so we said that quadratic function tables are tables of values characterized by constant second order differences of the output. Okay, so we had this constant 2 when we looked at the second order differences, which told us that this was a quadratic function we were dealing with. So this whole idea of a second order is really important, right? We're dealing with second order differences. We're dealing with a function that is written in terms of a second order polynomial, meaning that the highest exponent you see there, the highest degree, is 2, right? You have that x squared piece. So after we sort of figured all that out about quadratic functions, right, we figured out this whole idea of the second order difference, and then we talked about the general form of a quadratic, ax squared plus bx plus c, and how that was a second order polynomial, meaning it had that degree of 2. We then started to talk about, well, what does the graph of a quadratic function look like? And as it turns out, the quadratic function graph has a special U-shaped, which is called a parabola, and it looks like that, right? So when we graph a quadratic function, we see this special U shape called a parabola, and it can be either facing up like a U, or it could be flipped, and it would be facing down, sort of like an A, okay? It can go in either of those directions. And we said that parabolas are very special. They have what's called a focal point, and because of this, they can be used for satellites, telescopes, flashlights, and many other devices, right? Here's a satellite, and you can see the shape of a parabola inside. We also see parabolas in architecture, like in bridges. Here's the Golden Gate. It's got a parabolic cable. It's made with parabolic cables. And we use quadratics to model projectile motion, like throwing and launching of objects, like here a basketball. Right? The basketball goes up, 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 and then it's going to reach a maximum height and start to go down into the hoop. Again, kicking a football, right? You're going to kick that football. It's going to go up, 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 and then come down. Gravity's going to pull it down. So we see this parabola shape with projectile motions, which means that we can use a quadratic function to represent this type of motion. And we can also use quadratics to describe revenue, profit, and cost functions in business, okay? And here is one such function, all right? So quadratic functions are actually very, very useful in the real world and in everyday life. We can use them for all of these things that we see all the time. Now I'd like to take a minute and just talk to you guys about the coefficients that we see in our quadratic functions. They are very, very important. So it's important that you guys know what they are and that you can find them quickly and easily. And what even are these coefficients that I'm talking about? Well, they're that A, B, and C, those constants that we see in this general form here, right? Y, or f of x, equals ax squared plus bx plus c. The coefficients here are those constants, A, B, and C, okay? And it's really important that you guys can be given a quadratic function and quickly and easily identify what those coefficients are, what A is, what B is, and what C is. Because like I said, they give us a lot of important information about the function and the graph, right? We can call them constants, but we also call them coefficients, all right? So you'll hear me use both of those terms. So let's just take a minute and sort of look at some quadratic functions and quickly and easily figure out what the A, B, and C are. So I have a table. There's 3 different quadratic functions here, and I want to go through and talk about what A is, what B is, and what C is, what those coefficients are in each of the quadratic functions. So let's start with this first one, f of x equals x squared plus 4x minus 3. Okay. I might say to you, okay, what are the coefficients in this quadratic function? What are A, B, and C? Well, we know that A has to come before that x squared term, right? So it's the coefficient in front of our x squared term. Well, here's our x squared term. What's the coefficient in front of this? Well, it's actually an invisible 1, right? When we don't see a number, but we have the x squared, it means that there is 1x squared. It's the same thing as having that invisible 1. So here our A is 1. Okay, well, what's our B? Our B comes in front of our x to the first term, our x term. So we look at our x term here, what's coming in front of it? A 4. So our B is 4. And then finally, our C sort of hangs out by itself at the end. That comes in front of our x to the 0 term, which means that it's just going to be a number. So if we look at the end of our quadratic function here, where there is no variable, we see no x, we have a -3. And it's really important that we take that negative sign with us, right? A positive sign is sort of implied, like we know this is a +1, and we know this is a +4. We don't have to write those in. But if we have a negative, we need to make sure that we take that negative sign with us when we're thinking about our coefficient c there, okay? So there's our a, b, and c for our first quadratic function. So now let's look at our second quadratic function, which is f of x equals -4x squared minus 12x plus 9. Okay, again, what's our a? Well, our a coefficient always comes in front of our x squared term. So in front of our x squared term, we have a -4. All right, what's our b? Our b always comes in front of our x to the first variable. So it's going to come in front of this x term here. It's got to be -12, and notice again, I took that negative with me. I'm taking the negatives with me, I always do. Okay, and then what's our c? Our number, our constant just hanging out at the end here, right? It just hangs out at the end. It's +9, so 9. All right, so there's our a, b, and c. And let's look at one more, and this one's going to look a little different, but it is still indeed a quadratic function. All right, let's look at our last function here. F of x equals 10x squared minus 22. Now you'll notice there's no term in the middle. There is no sort of bx term, right? We just have an x squared term and then our constant at the end. So there is going to be no b here. So when we go to identify our coefficients, well, our a, again, we know our a always comes in front of our x squared term. So here our a is 10. Okay, but we go to look for our b, and you guys, there is no, we know our b comes before our x to the first term there, and we have no just plain x term. It's sort of like we have a 0x there, right? 0, there's nothing there. 0 times x is just going to give us 0. This is going to go away, all right? So our b here is 0, all right? We have no just x term, and so our coefficient there must be 0, right? It's zeroed out. And then, of course, what's our c hanging out at the end, our constant at the end here? Well, it's -22. All right, so our a is 10, our b is 0, and our c is -22. So if one of your pieces is missing, you guys, there's a 0 for your coefficient. All right, and I really wanted you guys to see that, so it didn't take you by surprise. So it's really important to be able to look at a quadratic function and to quickly and easily identify a, b, and c. So if that's still confusing you, I would like you to go back, rewatch this slide until it sort of sinks in and you start to understand how to quickly and easily do that. You're just looking at the numbers in front of each of your terms, okay? So why did I spend 5 minutes on the last slide making sure you could identify A, B, and C? Well, you guys, they're really important, and they give us a ton of incredibly important information about the graph of our quadratic function. So if we're given a quadratic function and we go to graph it, there are a lot of important pieces that we need to be able to identify, okay? And the whole rest of this video is going to be about using those A, B, and C coefficients to sort of determine those important pieces of information. So it's really important that you can identify them. So let's start with something called concavity. All right, when we graph a parabola, when we graph a quadratic function of the form f of x equals x squared plus bx plus c, right, we're going to get that U shape, we're going to get that parabola. It can either be concave up or concave down. And that just tells us how our U is going to bend. Is it going to be concave up like a U or concave down like an A? So there's a really quick and easy way to tell whether it will be concave up or down, and it's all about that coefficient A, you guys. All you have to do is look at A, and you will immediately know if your parabola is going to be concave up like a U or concave down like an A. So if A is greater than 0, meaning if A is positive, right? When we identify the coefficient A, whatever number that is, 1, 2, 4, 8.7, whatever it is. If it's positive, that means the parabola is concave up, okay? So let's take a peek at that. So concave up means that we have this lovely U shape, okay, in our parabola. And so the graph that just popped up here is the graph of the quadratic function y equals x squared minus 10x plus 19. Well, what's the a here, you guys? A equals 1, right? A is the coefficient in front of your x squared term. It's like there's that invisible 1. A, of course, is greater than 1. It's positive 1. It's a positive number. So we know right off the bat that our parabola will be concave up because A was positive, all right? That's it. That's how you know what direction your parabola will be going. It's just like when we were doing linear functions, right? If we had a positive slope, we knew our line would be increasing. But if we had a negative slope, our line would be decreasing. It's the same idea here. If we have a positive A coefficient, our parabola is going to be concave up. But what if we don't have a positive A coefficient? So if A is less than 0, meaning if A is negative, the parabola is concave down, okay? And we get that sort of A shape. So if you look over here at this next graph I threw up, it's almost exactly the same as the first one, except it's got a negative 1 for A. So this is the graph of y equals negative x squared plus 10x minus 19. And here all my signs are switched. So I switched all the signs. They're the opposite. And now our graph is concave down, okay? So we look at that A term, the coefficient in front of our x squared, and we look at what that is, and it turns out it's negative 1, right? So that just tells us we have a negative A term, and our parabola is going to be concave down. It literally flips it to be facing down, right? Just like a negative slope made our linear functions decreasing. Okay, it's sort of the same idea. So the way, all you have to remember is positive A, concave up, negative A, concave down, all right? So now let's talk about the maximums and minimums of quadratic functions and their graphs, okay? And it's very closely related to concavity, which is why we're going to talk about this next. So again, if we're given a quadratic function in the form, that general form that we keep talking about, f of x equals ax squared plus bx plus c, well, we know that if a, that coefficient a right here, right, we know that if it's positive, if it's greater than 0, meaning if it's positive, the parabola is concave up, okay? We know that. We just talked about that on the last slide, okay? But that also means that that parabola has a minimum point. And what is it? I'll show you. There it is. That's the minimum point. And that should make sense, you guys, right? Because minimum, you think smallest, right? It's down here on the bottom of the graph, okay? Minimum point. Well, conversely, if A is negative, right? Again, we just talked about. So if A is less than 0, meaning it's negative, this A term right here, if it's negative, well, that means the parabola is concave down, which we just talked about, shaped like the A, and it has a maximum. And what is the maximum? It's that top point. All right, so if we have a parabola that's concave up, we're going to be dealing with a minimum, okay, of a bottom point. If we have a parabola that's concave down, we're going to be dealing with a maximum, a top point. And that should sort of make sense in your mind, right? You think maximum, you think biggest, you think minimum, you think smallest, okay? So concavity is also going to tell us whether or not we're dealing with a parabola that's got a minimum or a maximum. Well, as it turns out, those maximum and minimum points, they have a special name. They're called the vertex of the graph. A vertex can either be a maximum or a minimum, okay? If our graph is concave up, the vertex will be a minimum. If our graph is concave down, the vertex will be a maximum. So I want to take a look at one of the graphs that we saw on the last page. It was the graph where we had a minimum, right? Our parabola was concave up. Okay, so we were dealing with a minimum point. That means that we are dealing with a vertex that is a minimum. So this point is called the vertex, okay? In this case, it is a minimum. Our vertex is a minimum. It's that bottom point, all right? And it is actually an ordered pair. It's a point, you guys. It's an XY point. That's important. So that means we want to figure out what is this ordered pair? What is this point that represents our vertex? How do we find it? And there's a special formula that we're going to use to find that vertex, okay? So we need to find both the x coordinate of the vertex and the y coordinate of that vertex, right? We need to find the x and the y, all right? So here's how we're going to do it. The x-coordinate of the vertex is equal to negative b over 2a. So again, knowing how to quickly find those a, b, and c coefficients is really, really important because we're now going to use them to find all these different pieces of our parabola. So to find the x-coordinate of the vertex, we need to plug in whatever our b value is and whatever our a value is into this formula, negative b over 2a. That's going to give us just our x, okay, you guys? We also need a y, right? We're looking for an ordered pair here. This is a point on the graph. We need an x and a y, right, to graph that point. So how do we find the y? Well, whatever value we get for x here, after we solve this equation, whatever value we get for x, we're going to plug it in to our function, all right? So if we got 2 for x, well, then we'd plug 2 in and to find our y. So this just reads that our y-coordinate of our vertex is f of whatever our x-coordinate was, okay? Our x-coordinate is negative b over 2a, so whatever we get when we do that, we have to plug it into our function. That's all that says. And it's going to be a lot more clear in a minute. We're going to actually do an example. So let's look at this example that I have right here on the screen, okay? This function is y equals x squared minus 10x plus 19. Here it is, okay? The first thing I'm going to do, and the first thing you should always do when you're dealing with a quadratic function and you're trying to graph it, is you should write down your a, your b, and your c. Okay, so I'm going to look at my quadratic function here, x squared minus 10x plus 19, and I'm going to find my a, my b, and my c. I know my a is the coefficient that comes before my x squared term. It's that invisible 1, so my a equals 1. I know my b is the coefficient that comes in front of my x term, which is negative 10, so my b is negative 10. And I know my c is that number that just sort of hangs out at the end, that constant that hangs out at the end. It's technically in front of my x to the 0 term, okay, which is just 1. So here, that constant hanging out at the end is a positive 19. So my c equals a positive 19. Now I have my a, my b, and my c, and I can start using them to sort of figure out different pieces, right? So let's figure out the vertex. Well, I know that the x-coordinate of the vertex is equal to negative b over 2a. Well, I said that my b was negative 10, right? So here I have a b. I'm going to plug in my negative 10 wherever I see a b, okay? So the x-coordinate of my vertex is negative b over 2a. So I have my little negative sign here, and then where my b was, I plugged in a negative 10. My 2 is going to stay, and now I need to plug in my a, okay? My a here was 1, right? So I plugged in a 1 there, all right? 2 times 1 is just 2, which leaves me with 2 right there, okay? That's my next step. Then I decided I just have to use some algebra, right, to solve from here. I was going to do negative 10 divided by 2, which gives me negative 5. I can't forget this negative sign that I had hanging out in front. Those two negative signs are going to cancel, and that leaves me with just 5, okay? So the x-coordinate of my vertex is 5. I'm not done, though, because remember, the vertex is a point, which means I need an x-coordinate and a y-coordinate. I've found my x-coordinate, it's 5. I now need to find my y-coordinate. And just like we did in the last 2 chapters, whenever we had an x and we were looking for a y, we simply plugged that x value into the function. So what do I mean by that? Let me clear some of this up so it's not so messy. Okay, well, to find the y-coordinate of my vertex, I'm simply going to plug the x value that I just got into my function, right? Here's my function, x squared minus 10x plus 19. So wherever I see an x, I'm going to plug in the value 5, okay, which gives me 5 squared plus 10, or minus 10 times 5 plus 19, okay? I just simply took this 5 right here and I plugged it in everywhere I saw an x in my function, okay? So 5 squared is 25, 10 times 5 is 50, 19 is just going to stay 19, 25 minus 50 is negative 25. Negative 25 plus 19 is negative 6. So now, you guys, I actually have an x-coordinate and a y-coordinate, which means that I know the vertex. The vertex is going to be the point 5, negative 6, right? I plug in my 5 for my x-coordinate. I solved to find negative 6 for my y-coordinate. And if we look at this graph up here, you guys, let's look at my graph up here. Well, that looks pretty good, right? Let's go over 1, 2, 3, 4, 5, and down 1, 2, 3, 4, 5, 6. And yeah, that does bring us to this point right here. Okay, so I went over 5 and down 6, and there it is. All right, 5, negative 6. So that is how you find the vertex, okay? You're going to plug it in. You're going to plug in your A and B values. You don't really need C to find the vertex. To this lovely formula to find your x-coordinate, and then whatever you get for your x-coordinate, you plug into your function, right, to find your y. All right, so that's how you do it. So remember, it's important to understand that a vertex is a point, which means it needs an x-coordinate and a y-coordinate. And what point is it? Well, it's either the minimum if you have a parabola that's concave up, or if our parabola had been concave down, it would have been the maximum point. All right. So now let's talk about something called the axis of symmetry. Now, you guys, if you look at a parabola, it is beautifully symmetric, right? We could literally cut that parabola in half, and if we reflected it, it would be the same on both sides, okay? And when I talk about cutting that parabola right in half, right? So if we just drew a line and then cut it on that line to cut it in half, I'm actually talking about the axis of symmetry. The axis of symmetry is the vertical line that goes through the vertex. So I'm talking about the line through which this parabola would be symmetrical. And your axis of symmetry always goes through that vertex. It's always going to go through that like center point, okay, which should make sense. If we want to cut it in half, we have to cut it right down the middle. The vertex is the point at the direct center of our parabola, right? At least on the graph of our parabola, I should say. And so this axis of symmetry is that vertical line that's going to go through the vertex. It's the line that's going to cut our parabola in half. Well, we can also say it's the line that is of x equals negative b over 2a. That should look really familiar, right? We just used this formula, negative b over 2a, to find the vertex, this point right here, to find the x-coordinate of the vertex. All that's saying is that the axis of symmetry goes through, it's the line that goes through the x-coordinate of that vertex, right? It's the line that's going to go right through, right there. It's going through the x. See how it hits the x-axis? It's a line. That's why our line is x equals negative b over 2a, because it's that vertical line that's going through the vertex, okay? So it has to have the same x value as our vertex. So if we are trying to figure out what the axis of symmetry is, let me show you again. How would we do that? Let's look at the same example we've been working with. This function, y equals x squared minus 10x plus 19, okay? And I told you the first thing you always want to do before you start graphing your quadratic function, your parabola, is you always want to identify your a, b, and your c, right? We know that a equals 1, b equals negative 10, c equals 19, but it bears repeating. You should always, always, always find those first. Okay, if we want to find the axis of symmetry, we know it's the line x equals negative b over 2a. Again, let's plug in negative 10 for b, 1 for a, and what does that give us? No big surprise here, x equals 5, okay? We don't have to go any further. The axis of symmetry is not a point, right? Our vertex was a point, so we needed to find a y-coordinate to go with it. This is just a line. It's just the line x equals 5, okay? So the axis of symmetry is the line x equals 5. If we look at our graph, there it is. Axis of symmetry, x equals 5. So it's just this line that cuts our parabola in half. So if we reflected our parabola over that line, we would get the whole graph, right? It'd be identical from one side to the next, okay? It's symmetrical. It's the line that makes our parabola symmetrical. That's why it's called the axis of symmetry, okay? And it will always go through the x value of your vertex, okay? Notice we got our vertex here was 5, -6. Well, the axis of symmetry is just the line that goes through x equals 5, okay? Because of course it has to go through the vertex, right? Our vertex is right smack dab in the middle. All right, so that is the axis of symmetry. Another very important piece of our graph. So if you are so far following along, you understand how to find these coefficients A, B, and C. You understand how to find concavity. You know, if it's concave up or concave down, if you're dealing with a maximum or a minimum. You understand what the vertex is talking about and how to find it, and the axis of symmetry and how to find it. You can just totally skip this slide. You can jump ahead to the next slide, okay? If you would like some more practice, okay, because I know I just threw a ton of information at you. So if you want some more practice, you can use this slide to do so, all right? You can pause it. You can look. I put 3 different quadratic functions here, and I wrote in the information for you what the A equals, what the B equals, what the C equals, what the concavity is, if it's concave up and we have a minimum, or if it's concave down and we have a maximum, how to find the vertex and the axis of symmetry. So if you are still not comfortable with any of those pieces, I would pause right here, start at the first function, okay, and just see, where did this 1 come from? Where did this 4 come from? Where did this -3 come from? Oh, wait, right. This must be concave up because our 1 is positive, our A is positive, so we're dealing with a minimum, okay? How did I find the vertex? All right, here's my x-coordinate of my vertex. Here's the y-coordinate of my vertex, all right? So here's my vertex. And the axis of symmetry is, of course, the line that goes through that x-coordinate. So if you are not sure, pause here. Go through each one of these, work through them. The answers are right here in front of you, and this will just give you a little bit of extra practice, okay? Once you're done with that, unpause the video and move on and listen to the rest of the slideshow. So surprise, surprise, we are now going to talk about y-intercepts for quadratic functions, right? This should be no big shock for anybody. We have talked about y-intercepts for basically since day 1 of this class, right? For every sort of function that we've done. When we did linear functions, we saw y equals mx plus b, right? B represented the output for our y-intercept, right? And when we talked about exponentials, we saw that the a value, so y equals a times b to the x, right? The a was our initial value, which was our, of course, y-intercept. So y-intercepts are incredibly important, right? They represent our initial value for our function. They're very, very important. They give us a lot of great information. So of course we're going to talk about y-intercepts with our quadratic functions. So let's talk about how we find our y-intercept, okay? Well, we know that the y-intercept is, of course, the point at which our function crosses the y-axis. That should come as no big surprise. I don't know why I drew that arrow there, right? The point that our graph is going to sort of cross this y-axis, and I'm going to have to extend this up to sort of think about where this graph is going to hit it, okay? So it would be this point, right, where our graph sort of intercepts our y-axis there, okay? How do we find it when we're dealing with a quadratic function? So the y-intercept of any parabola is the point 0c, okay? So any parabola of the form, right, f of x equals ax squared plus bx plus c, well, our y-intercept is simply the point 0c. So whatever your c value is, whatever that coefficient is, okay, that's what your y value will be. That's where your graph is going to hit the y-axis at that point. All right, and that should make sense because remember, when we're looking for an intercept, right, we plug in 0 for the opposite. So if we're looking for the y-intercept, we're of course plugging in 0 for x, okay? And if we have the function ax squared plus bx plus c, and we plug in 0 for x, that means a times 0 squared plus b times 0. I'm just plugging in 0 everywhere I see x plus c. Well, 0 squared is 0, and a times 0 is going to be 0, so that's going to go away. B times 0 is going to be 0, that's going to go away, and you're just left with c, okay? So the y-intercept is 0c, okay? which is going to make it really easy, you guys. This is why I keep saying, always find your A, B, and C coefficients first. It's going to give you so much information, right? The second we find C, we've also found the y coordinate for our y-intercept, all right? We've basically found our y-intercept. So again, if we look at this same example that we've been looking at since the beginning, y equals x squared minus 10x plus 19, well, C equals 19, you guys. So the y-intercept is 0, C, which means it's 0, 19. All right, that should make a lot of sense. And again, here's some proof if you don't quite believe me yet. All right, again, if I'm looking for the y-intercept, I'm plugging in 0 for x. So everywhere I see an x, I'm going to plug in 0. So that means f of 0 is going to be 0 squared minus 10 times 0 plus 19. Well, 0 squared is 0, so that's going to go away. 10 times 0 is 0, so that's going to go away, which just leaves us with 19. All right, so our y-intercept is 0, 19. All right, and that should make sense for this graph. This point up here is going to be 0. We're going to be up on 19, all right? That's where this particular parabola is going to hit the y-axis. It's going to intercept the y-axis, okay? So it's really nice. It's not too bad to find a y-intercept for a quadratic function because it's literally just this c value, right? It's a 0, and that c value gives you the ordered pair that you need right off the bat. Well, this should also come as no big surprise. Now we're going to talk about x-intercepts, right? We always talk about y-intercepts and x-intercepts. And we saw for linear functions, we typically had one x-intercept. The only exception for that was when we were dealing with a horizontal line, okay, where it was just a line straight across going through some y value, okay, which of course it's never going to intercept the x-axis. That was the only exception for that. When we looked at exponential functions, we had no x-intercepts because it turned out that the x-axis was actually an asymptote, which means while our function got really forever and ever and ever got closer and closer and closer and closer to the x-axis, it never actually hit it. Okay, so there were no x-intercepts for exponential functions. Well, what about for quadratic functions, right? So quadratic functions can have 0, 1, or 2 x-intercepts, okay? This is the point, right, where y equals 0. So you're looking at x0. So it's the point or points, x0. X-intercepts can also be called zeros or roots. You'll hear them referred to that in our book when mathematicians talk about them. Okay, so x-intercepts of quadratic functions can also be referred to as zeros or roots. So when you hear any of those terms, it means the x-intercept of a quadratic function, okay? So let's look at that. Let's look at each case. So this first graph here, okay, has two x-intercepts, right? An x-intercept is where your graph is intercepting the x-axis. So here's one, and here's one. So this is a graph of a parabola with two x-intercepts, okay? Two solutions, two roots, two zeros, all right? Okay, let's look at the second graph. Well, this is a graph of a parabola with only one x-intercept. And as it turns out, the only time that a parabola has one x-intercept is when the vertex is on the x-axis, okay? And that should make sense. If the highest or lowest point is right on the x-axis, it's only going to intercept it at that one point, all right? And then if we look at the third graph over here, this is a graph of a parabola where we have 0 x-intercepts. You look at this graph and it does not hit the x-axis at all. It never crosses it, all right? So we have no zeros, no roots, and actually, as it turns out, they're imaginary. They're complex numbers, those zero roots, but that's not something we're going to go too in depth into right now. For now, I want you to just understand that quadratic functions can have 0, 1, or 2 x-intercepts, which begs the question, how do we find them? Okay, with quadratic functions, the x-intercepts are very important, you guys. So we want to be able to find them. We need a systematic way to find them. And there is a really nice formula that allows us to do just that. And we're going to talk about that on the next slide. So how do we find x-intercepts? Well, if we want to find the x-intercepts, which remember are a point, right? It's the point, or points, I should say, point or points, x, 0, okay? We want to find the value for x. How do we know the value for y? We know y is 0, okay? We need to find the x values of these points. How do we do that? Well, we use the quadratic formula. So when we're trying to find the roots, the zeros, we use something called the quadratic formula, okay? And I'm sure you guys have heard this somewhere around the block. It's okay if you don't remember it, but the quadratic formula says that this x value or values is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So again, I said it was so important to be able to find that a, b, and c right off the bat. You guys, we've used it for almost every single piece of important information as we've talked about this, right? And we are going to need to know a, b, and c to use this quadratic formula, right? You see A in here, you see B in here, you see C in here, right? Oh, and here's another A. So it's really important to be able to find those right off the bat. When you are given a quadratic function, the first thing you should do is look at those coefficients and say A equals this, B equals this, and C equals this, okay? So again, let's look at this function that we've been looking at this entire time. Y equals x squared minus 10x plus 19. And let's find those x-intercepts. So we have 2 for this function, right? 1, 2. So we're looking for these 2 points. So we know that the y value is of course 0, right? We're not going up or down on the y-axis at all. But we don't know the x value. And we do know that we're looking for 2 x values. 1 for this point and 1 for that point, okay? And you'll notice that comes from the plus and minus, right? That's why there's a plus and minus. One of those x values is going to be negative b plus the square root of b squared minus 4ac over 2a, and the other x value is going to be negative b minus the square root of b squared minus 4ac over 2a. So that's why we have that plus and minus there. Okay, so let's look at that function. We have this function x squared minus 10x plus 19. Our a is, of course, 1, our b is, of course, negative 10, and our c is, of course, 19. So now we're going to take those values a, b, and c and plug them right into this beautiful formula to solve for x. So we know x equals negative b plus or minus b squared minus 4ac, all right, which means I'm just going to take this and I'm going to rewrite it and plug in my a, b, and c, all right? So x equals negative, I have to write that negative sign, b. And here my b is what? Negative 10, so I plug it right in there. I have to write plus or minus the square root of b squared. Again, b is negative 10, so I plug it in there. Notice I put parentheses around negative 10 so that I remember to square the entire quantity of negative 10, okay? Minus 4 times a here is 1, times c here is 19, all over 2a. Okay, 2 times 1 is 1. All right, so I've now plugged that in. I've plugged in all my numbers. That's sort of the easy part of this, right? Simply to plug the numbers in. Now I have to actually solve this big old gobbledygook mess here, all right? That's sort of the more challenging part of this, and but we know how to do it, right? We learned PEMDAS, and when we were working with PEMDAS in Unit 1, we actually saw problems just like this. And that's why we worked with those problems in the very first unit, so that when we got to this one, we knew how to tackle them, okay? So the first thing that we need to do, you guys, is to work with any sort of grouping, right? And actually, I shouldn't say PEMDAS because we called it GRMDAS, right? G for grouping. And the biggest grouping that pops out at me is, of course, this whole big square root gobbledygook. So I am going to tackle that first, okay? So the first thing I need to do is figure out what's underneath here. So I'm going to work with my negative 10 squared first, which gives me 100, okay? And then 4 times 1 times 19 is going to give me 76, all right? So that leaves me with negative 10 plus or minus the square root of 100 minus 76 all over 2 times 1, Right, now I'm going to simplify that grouping. Okay, I know it's a grouping because it's underneath the square root. 100 minus 76 gives me 24. So guys, you always want to tackle everything underneath the square root first, okay? Leave everything else alone. Don't even look at these pieces yet, okay? Tackle this first, all right? Get it simplified. Start there. Okay, so when I tackle that, that leaves me with the square root of 24. Notice I'm still just dealing with this one piece. I haven't touched this or this yet, okay? The square root of 24 is about 4.9, all right, which is where this number came from. I rounded, just so you know. It's some ugly number, the square root of 24, I rounded to 4.9. All right, that's where that number came from. Now that I've dealt with that large grouping, I can now move on to deal with the other stuff, all right, the easier stuff. So I see that a negative 10 is going to just leave me with positive 10, and 2 times 1 is, of course, 2. Okay, so that's where this next step is coming in. Now, you'll notice that it says x equals 10 plus or minus 4.9 over 2, meaning I have two cases, 10 plus 4.9 over 2 and 10 minus 4.9 over 2. So I'm now going to split this up into those two cases and deal with one at a time. So let's look at this case first. This is my x equals 10 plus 4.9 over 2. All right, 10 plus 4.9 is 14.9 divided by 2 gives me 7.45. So there's one of those x values. Okay, there's one of them, one of those x values that we were looking for up here. All right, now I need to do x minus 4.9 divided by 2. So excuse me, x equals 10 minus 4.9 divided by 2. So 10 minus 4.9 is 5.1. 5.1 divided by 2 is 2.55. So there's the x value of my other x-intercept. So now I've found both x values for my x-intercepts, you guys. 7.45, 2.55. So that means that I have an x-intercept at the point 2.550 and 7.450. And again, if we look at our graph, that should make a lot of sense, okay? That should be pretty clear. All right, there's 2.550. And yeah, look, 1, 2, it's about in the middle of 2 and 3. All right, 2.550. And then 7.45 is about in the middle of 7 and 8. All right, 1, 2, 3, 4, 5, 6, 7. Yep. So there are the values of my x-intercepts. So it's sort of an ugly formula. I will definitely give you that. It is an ugly, ugly formula. But it's also a very important formula. And, you know, once you do a few of these, you'll start getting into a rhythm with it. But the important thing for you to remember is that this formula is only to find the x value for your x-intercepts, okay? The y value is always going to be 0 because it's an intercept. So this formula just represents your x value. That's important, okay? Don't get confused. And when you do this formula, when you plug in your a, b, and c and you tackle this formula, always, always, always start with everything underneath the square root. Start with that piece first and work your way down from there. And don't forget that you need to split it up into the plus and the minus cases once you sort of get to that bottom. Right? Once you sort of worked out a lot of the math, you need to split it up into the plus and the minus. You're going to have two different cases here, okay? That's important. Okay, so that is how you find the x-intercepts. So again, that A, B, and C, so important, you guys. So important. Okay, so now let's put it all together, you guys. We learned so much about graphing quadratic functions today and all these little pieces of very important information. So right, when we have a quadratic function of the form ax squared plus bx plus c, which we have right here, y equals x squared minus 10x plus 19, the first thing you should always do is figure out your coefficients a, b, and c, right? So here we have a coefficient of a equals 1, b equals negative 10, and c equals 19. All right, we learned that the graphs of these parabolas can either be concave up or concave down, and that depends on whatever the value of your a coefficient is. So if your a coefficient is positive, like with this graph, your graph is concave up, right? It's making that nice U shape. If we had had a negative a, our graph would have been concave down. All right. The concavity of our graph also tells us whether or not we're dealing with a minimum or a maximum. So since our graph is concave up, we are dealing with a minimum, right? That lowest point there, which is the vertex. All right. Your vertex will either be a minimum or a maximum. Since our graph is concave up, our vertex is a minimum. For our graph, our vertex is 5, -6, and we found that by first finding the x value, which was equal to -b over 2a. That gave us 5. And then we plugged in that 5 to our function, x squared minus 10x plus 19, right? Everywhere we saw an x, we plugged in 5, which gave us -6, okay? So that's how we figured out the ordered pair for our vertex. We also talked about something called the axis of symmetry, which is just the line that goes through your vertex. It's the line that cuts your parabola in half. So for our graph, our axis of symmetry was the line x equals 5. Okay, that line goes through our vertex, so you'll notice x equals 5. It's the same value as our x value of our vertex, okay? And it's just cutting our parabola right in half. We then talked about the y-intercept. The y-intercept is just the point 0, c, okay? So if you know what your value of c is, you also know your y-intercept, okay? For our graph, it's 0, 19, because 19 is our value of c, which means it's going to hit our y-axis up here at 19, 0, 19, okay? And then we talked about, of course, x-intercepts. We know that quadratic functions can have either 0 x-intercepts, 1 x-intercept, or 2 x-intercepts. This particular parabola has 2 x-intercepts. There they are. Okay, and how did we find them? We use the quadratic formula, which says that x is equal to -b plus or minus the square root of b squared minus 4ac, all divided all over 2a, right? That will give us our x value. And of course, our y value is 0 because we're dealing with x-intercepts here. Okay, so that is graphing quadratic functions. I hope this was helpful. And if you have any questions, please always reach out. I am here. All right, you guys, take care. Goodbye.